Anyway, yeah, thank you very much for gathering for the annual event, CaMa-Flood Annual Progress Briefing 2025. So I'm Dai Yamazaki, primary developer of CaMa-Flood, and I'd like to welcome all of you for today's event. And Anyway, thank you very much for contributing to CaMa-Flood researches or being interested in our activity. So, primary purpose of this annual briefing is to highlight the research using CaMa-Flood, mainly published in 2025, and to make the achievement visible among the CaMa-Flood community and beyond. And today, we have 14 talks introducing the CaMa-Flood journal paper. So, I hope everybody can enjoy today's meeting. Okay. And I'd like to appreciate a lot for the contributors who cooperated to make the annual report. And now the PDF version of the Progress Report 2025 is available in CaMa-Flood webpage. So this is also today's program. So please access and download the annual report. And this is also accessible from the annual progress meeting webpage. And thus this PDF report contains links to the all papers. So if you are interested in the talk today, please check the originally published paper for the details. And in this online meeting, this is recorded to make a video report. So this will be uploaded to the CaMa-Flood webpage later, after the editing is done. Okay, and this is a message for presenters. So please be precise on your talk time. And we appreciate if you provide a brief summary and highlight them because all the papers are already published. All audience can check details in the published paper. And for participant, sorry, today I think we don't have adequate time for question and answer. So please ask your questions using Zoom chat. And presenters, after your talk, please try to respond to them. Thank you very much for cooperation. Okay, and I'd like to review today's program. First, we'd like to provide a summary of a CaMa-Flood core development in 2025 in 40 minutes. And after the brief report by myself, I'd like to invite Dr. Zhao from Science Tokyo and Mr. Shengyu Kang from Wuhan University as a highlight development for last year, 2025. And next, we'll do the review for the CaMa-Flood application papers. So we have 6 talks in these sections. And after that, we will do review on the CaMa-Flood development papers. And we have 5 more talks for this section. Okay, so I'd like to start my own session 1, starting from my own talk. So session 1 is a status of CaMa-Flood core development. And I'd like to report the major update. And first of all, good news is, we have published the CaMa-Flood review paper in AOGS Geoscience Letters in December. So the paper is entitled Advancing Global River Hydrodynamics Simulations by Catchment-Based Macro-Scale Floodplain Modeling Approach. And this is a very first, review and summary paper of CaMa-Flood development based on the AOGS Committee Distinguished Lecture in 2021. So this paper summarized the basic principles of CaMa-Flood models and the advancement of global river hydrodynamic simulations. And also, it reviewed and introduced a wide range of application studies. And primary findings from this review paper is that CaMa-Flood is still one of a few global river models which can represent very basic principles that water flows from higher place to lower place. And second findings is using catchment-based approach, we can do realistic representation of river discharge, water level, and flood extent. And actually, this approach is not only for CaMa-Flood. So there are several other models using the same approach, achieving how to say, same realistic simulations. And third, the CaMa-Flood model has high simulation accuracy and adequate computational efficiency and flexible usage, commit to various applications, not only flood risk assessment, but also climate and biogeochemistry modeling and integration with satellite observation. So anyway, these findings are summarized in this review paper. So I hope you can enjoy this paper. And I'd like to introduce the last year's development. And one happy news is that CaMa-Flood version 4.30, the very latest version, is released yesterday, 12th March 2026. So you can now access to the latest version in the CaMa-Flood web page. I have to note the web page URL was changed, so now it's in Yamazaki Labo web page. And the major update in version 4.3 is the levee protection scheme. And this is, detail is reported by Zhao in G2 sessions. And the second major update is a new tracer scheme, which assumes a well-mixed tracer. But anyway, we can do a tracer calculation in CaMa-Flood. And the third major update is a calculation speed up by quasi-sparse matrix and OpenMP plus SIMD. So I'd like to briefly introduce these ones. So the tracer scheme it's included in this directory. So this is a very simple tracer scheme, assuming a well-mixed tracer. So tracer runoff or anyway tracer mass is given from a random grid as an input file, and then we calculate tracer concentration, assuming how the tracer is well mixed in a grid cells. And it calculate the tracer flux following the river flux. So this is a very simple model. But now we can do, for example, nutrient flux calculations or microplastic transport in rivers. Or we can also assess the flood cause by using, for example, by putting some colors to the waters. So we can discuss whether the flood is caused by typhoon or snow melt or etc. So the new tracer scheme can be used for this kind of applications. And second major update is the speed up by quasi-sparse matrix and OpenMP plus SIMD. So this is a bit technical, but what we did is we totally changed the calculation algorithm. So previously, we use the above equation, but this equation have to, how to say, search the upstream grid cell of each grid cells. But we found out this algorithm is actually very slow because we have to use OpenMP atomic calculation to avoid memory access collision. But instead of original methodology, we found that the using sparse matrix, we can use more rough equations, which sum all grid cells, upstream grid cells to downstreams. But by allowing at zero calculation using sparse matrix, we found we can avoid OpenMP atomic calculation, and this calculation can be much faster than original versions. And in combination with the SIMD, what we found is the version 4.3 can be up to 40 to 50% faster than the previous 4.2 versions. So this is actually a very good improvement compared to previous version. And in addition, we also developed a more efficient GPU version, and this is reported by Shengyu Kang in report G3. So please wait for that. Okay, so this is the input from myself, and I'd like to first ask Zhao to make a report on the new Levee scheme. Okay, so Zhao, could you please share your screen?
Yeah, thank you so much. I will share. Can you hear me?
Oh, yes. Could you please turn your video if possible? Okay, great.
I think it's okay now.
Mhm.
Okay, I will start. I'm very happy to share some of my research. And today, my presentation topic is developing a Levee module for global flood modeling with a rich level parameterization approach. And I'm Gang Zhao and from Science Tokyo. So actually, this work was finished when I was a postdoc researcher in U Tokyo with Yamazaki sensei. Okay. Yes. So over the past 2 decades, we have seen so many global flood models emerged capable of modeling flood dynamic for global river network. If you look at the left figure, it shows two kind of global flood model. The first is cascade model. That the model CaMa-Flood we use today is belongs to this kind of framework. It use global it use climate reanalysis data to drive land surface model, and the input of CaMa-Flood model is runoff. And based on the flood routine of CaMa, we could calculate the dynamic time series of river depth or flooded area at core resolution, and then use downscaling approach to get the high resolution flood extent and flood depth. Another kind of framework is gauge flow database model. For example, one of also popular model Fathom use this kind of framework. It directly uses gauge-based data to drive 1D, 2D high resolution dynamic model, and then we could get a high resolution flood extent directly. Um, if you look at this figure, show the flood extent from CaMa-Flood simulation from 2000 and 2028. When we compare with the MODIS daily observation of the same period, we could notice obvious overestimation. So we think this overestimation mainly because of the levee. So to reduce the negative impact of flood, numerous types of levee, such flood defense, such as dam and levee, have been built along all large rivers worldwide. For example, if you look at the left figure, we will find that all large rivers, such as Mississippi River, are protected by levee. Same phenomenon also happened in China and other regions worldwide. So how to considering levee into global flood modeling is a challenging and pressing task. So there are mainly two difficulties of considering levee into global flood models. The first is in real life, the levee system is very complicated. If you look at the left figure, it shows a levee system in the San Francisco, I remembered. So in real life, there are so many ring levee and the levee system sometimes not continuous. So it is very difficult to directly incorporate this kind of complicated system into modeling. The second is many regions still lack comprehensive levee database. The middle figure shows the location of region where have well recorded levee. This figure from one of our previous colleague Julian. In this figure, we could find that most blue color region are still lack enough levee database. So to incorporate levee into global flood model, we need on the one hand improve model, on the other hand develop the corresponding levee parameters. And so on the model aspect, we already developed a new levee model in the CaMa-Flood. So this model is a little bit simple based on the two basic assumptions. The first is the symmetric cross-section, which means that same levee height on both sides. The other is only one levee in one cross-section, which means that no secondary levee or ring levee of that unit catchment. Based on this assumption, generate two key parameters. The first is levee fraction. It represents the distance between levee to river. And the second is levee height. It represents the distance from the river bank to the levee top. These two factors mainly control the levee capacity. Based on these two parameters, we could easily incorporate it into the flood routine. In the right figure, we show the four scenarios when the water level from the river top to the overtopping. So based on the assumption of the CaMa flood, we could easily redistribute the flood storage inside levee and outside levee and do the same flood routine process as before. Now we already have the data. Next step, we need to think about how to calculate the levee parameters. And the first parameter is levee fraction. If with high resolution terrain data, it is very easy to extract the levee location. One of my colleague Kan-san already developed the algorithm to extract the levee height and the levee location from high resolution terrain data. This paper just published in the Geophysical Research Letter this year. And if some region without levee, luckily we found a very good regression. If you look at the right figures, we will find that the black line is the levee location. It's just located along the edge of the flood exposure, such as the crop area or urban area. Then I develop an algorithm to calculate the levee distance and or levee fraction based on the equation. The algorithm is a little bit simple and divided into three scenarios. For example, if only one side have levee, we calculate the distance from the river center to the nearest levee. And if both sides, we calculate the mean value. If during the searching path we found other river, we will stop the searching. And based on the equation, we could easily calculate the levee fraction, both either from the land use data or from the real levee observations. Sorry. So this figure shows a regression result by comparing the levee fraction based on the land use data and the real observation. We will find a very good regression. The NSE, national efficiency, is larger than 0.8 for 5 regions. I think this is a good performance because this algorithm don't rely on any parameters for calibration, which means that for any region worldwide, if there's an open access land use data, we could use it to calculate the levee distance and then convert to the levee fraction based on the equation I mentioned before. And this is the result of the levee fraction we calculate based on the high resolution land use data. We will find that large river or the lake region have the large values. And another parameter is the levee height. So in this research, we use the levee standard to estimate the equivalent levee height, not use the structural levee height. This mainly because if you look at the live figure, we will find that in real life, the levee height data is also very complicated. So this figure shows the real levee height in the US. We will find that the levee height is fluctuate from upstream and downstream. So it is very difficult to directly incorporate this structural levee height into modeling because of the different GeoID and also the basic assumption of this the real levee height and CaMa also a little bit different. Luckily, we already have this kind of levee standard data for global or national scale. For example, one of my previous research estimates the levee standard for all locations in the continental US, and for worldwide, we already have the FlowPros database. It covered almost all regions worldwide have this kind of data. Then we develop another algorithm to convert levee standard to the equivalent levee height. This mainly have two steps. The first is we do an initial simulation with a very high levee height. For example, we assume it. Oh, sorry, I drink. For example, we assume 100 levee height to a very high levee height. Then we run the model and do flood frequency analysis based on the simulated river water depth. And then we do a second simulation with using the updated levee height and repeat step 2 and 3 until the levee height stabilizes. And these figures show after 2 loops, the levee height will become stabilized. And this is good news because although we try to speed up the global flood modeling, it's still time consuming now. Based on this algorithm, we could calculate the equivalent levee height for global coverage. For example, in this figure, it shows that it almost cover all large rivers The levee height is mainly controlled by the two factors, the local flood hazard condition and also the local levee height, local levee standard. So, for example, if you the high levee mainly located in the, for example, middle Yangtze River or the downstream Mississippi is in our inspection. Now we already have levee parameters and also the corresponding model in the CaMa-Flood modeling. So the next is how new levee model will improve flood modeling. We select around 6 stations or 7 stations in the paper, but just show 3 most improvement station in this slide. We will find that after sorry, I don't know why. After levee implementation, the performance improve a lot, and the discharge also improve based after levee implementation, and the water surface elevation also improve. The most improvement mainly happened on the coastal area. This mainly because of without levee, the purification phenomenon happened. So the water will flow from a local river ridge to the nearby one. But when levee construction, this phenomenon deduced, and the most water actually stay in that location. So that's main the reason for the large improvement on this kind of station and the improve and the increase on the discharge and the water surface elevation. And this slide shows the improvement on the flood hazard mapping. This is actually what we most care about. We select so many stations, regions in US. I remember we select five regions in the continental US, and during the revision process, we add extra this kind of 8 region for a demonstration. We will find that without levee, the red color is the overestimation. It's still overestimation too much, but after levee implementation, this kind of overestimation significantly improve. This not only improve on the, this means that it's not only improve on the flood hazard mapping, and it also increase the flood hydrodynamic modeling. Okay, a brief summary about this research is that we already developed a levee model based on the CaMa-Flood modeling, and we try to propose a method to estimate the key levee parameters, include levee and protect fraction and the equivalent levee height for global coverage. So currently we could, how to say, use this kind of model to map, to simulate global hydrodynamic considering levee. For example, if we go back to this, the picture I showed previously, if you currently compare with the MODIS or daily observation, from 2000 to 2008, and with the CaMa levee simulation, we will find that the overestimation problem already can actually be solved. And we could conclude that incorporating levee representation could significantly improve model performance in predicting river flood extent and also other river hydrodynamic process. Thank you for your listening. And if we already actually released levee parameters for global coverage, so kindly turn on the levee model when you need it. Thank you so much. Sorry for
Thank you
my
very much,
voice.
Gan, for a very intensive talk and keeping a time. This Levee scheme is, as I mentioned, released yesterday, so you can try the new Levee scheme. Okay, and because of time limitation, so I'd like to say discussion is on chat. So if you have any questions, please send a message to Zoom chat. Okay, then next I'd like to invite Mr. Shengyu Kang from Wuhan University, and he developed a new CaMa-Flood GPU version, which is very fast compared to the original CPU version. So, Shengyu, please start your presentation when it's ready.
Hi, Sensei. Uh, could you hear me?
Mhm. Okay, please start.
Okay. First, thanks to Yamazaki Sensei to give me the opportunity to share our CaMa-Flood GPU, GPU-based hydrodynamic model implementation for scalable global simulations. So the situation is that we have a great global flood model named CaMa-Flood, and it works very great. But it takes days to run simulations on a GPU cluster. And I assume that everyone sees GPU are future, and I think all of you are using AI now. So they say that big AI models works due to GPU because GPU can do the matrix operation very fast. So why not CaMa-Flood GPU? Why not CaMa-Flood CPU use GPU? So our goal is to first understand how to use GPU, and we choose the good coding language, and then I need to implement. And first, let me briefly introduce some difference between CPU and GPU. CPUs are optimized for general purpose tasks with many small number of strong, flexible cores, but GPUs are designed for massive parallelism. Their hardware layout is built to run thousands of tiny tasks at the same time, which is ideal for matrix operations and other patterns we also find in physical models. So uh, to convert the code, porting function code to GPUs, we need to understand the logic differences between GPU and CPU. For example, taking the diagnosing water dips as an example, the CPU logic is that for each catchment, the CPU checks flapping layers one by one from the bottom to up, and it stops immediately upon finding the correct layers. But the GPU with calculations is not stopping. The processes thousands of catchments simultaneously. So the GPU threads work in synchronized groups, and the threads within the same warp are required to follow identical execution paths. And we are using Triton to speed up the development. Triton is part of powerful Python ecosystem, and it integrates well with the famous deep learning framework called PyTorch, and it is very fast since it has a magic compiler. Although Python is slow, but the slow Python code runs only once, while the fast Triton code runs hundreds of millions of times. And you can see that we just write some easy codes, just kind of high levels Python or Triton code, and the Triton compiles lowers the code to the low level .ptx codes, so it runs very faster on GPUs. And then we need to design a generalized GPU physical modeling frameworks, and we fully leverage the advantage of object-oriented programming to design a modular, extensible GPU components. So we have some abstract classes, such as abstract datasets handling the space matrix transformation and distribute data sharing. And we have abstract modules and abstract models. The abstract models controls the modules and some physical processes. And we structure the system as that way in many layers and modules. We have written all the codes from the input to output so that our modules support multi-bit GPU simulations. And because Python is a very modern language, we can write CaMa-Flood GPU in a very modern way. So it is very easy to modify and add some new features. Uh, but rewrite the CaMa-Flood to the CaMa-Flood GPU, it's not so easy because CaMa-Floods work on a irregular catchment-based graph, not a uniform grid from the land surface models or climate models. So the upstream to downstream dependencies in CaMa-Flood lead to memory conflicts on the GPU. The memory conflict handling is complex under the hood, but it is a very classic problem. And we can just use the faster API solved by the CUDA system or Triton system. and we just use the function to get the solution. And the this approach would have each downstream cell loop over all its upstream neighborhoods and sum their contributions. And this tend to be slow and also complicated to parallelize. Our solution is to switch a parallel scatter at formulations. Each catchment contributes its outgoing flux and then scatters this value directly to the appropriate downstream storage location using the starter add operation. And we just use efficient pipelines. The straightforward method is one-step data loading, one-step simulating, but in CaMa-Flood-GPU, because we are using Python, the Python can give give us more opportunities, so we can load bunched graph data, and we can synchronize GPU, use broadcast, and collect the message using the research across all the GPUs. Uh, so everything in CaMa-Flood GPU is very graceful, I think. So before talking about the performance, we must ensure the scientific reliability. We carefully compare the GPU version against the original CPU CaMa-Flood under both simple and bifurcation networking configurations. The map and the hydrograph shows that numerical differences are extremely small, typically within floating point running years. So using CaMa-Flood GPU does not introduce notable bias, and you can just use it. Let's look at the speed and cost. We benchmarked 1 year global simulations at different temporal solutions. So we can see that using the price from the Wuhan University Supercomputing Center, we can compute the approximate cost of each run and found that using our CaMa-Flood GPU, we can save very much money. The cost drops about 96%, 1970%, yeah. So at high resolution, you can how to say, you can get your results in hours instead of days. So in practice, it means that you can afford to run many more scenarios and explore different parameter set of climate forcings. And for the future, uh, uh, we can see we have multiple backends for our CaMa-Flood GPU. For now, the official release of CaMa-Flood GPU is supports the NVIDIA GPU, the AMD GPU, and for now we have Apple GPUs. You can imagine that using the MacBook Air, just the laptop. I'm talking, and after 1 minute, you can get the global hydrodynamic results. Yeah, I think it's very amazing. And another Another plan is that we can represent a GPU accelerated differentiable river routing framework built on the CaMa-Flood by fusing the primary physics and the forward mode tangent linear computations into single Triton GPU kernels. We just obtain exact analytically gradient of discharge with respect to the Manning coefficient or Ralph correction factors or just channel geometries, but it's just an initial plan. Uh, so only use our fast GPU frameworks, we can do much more iterations using some algorithm like the gradient descent algorithm. Yeah, we can get better results and get better parameter calibration. Yeah. Oh, thanks for your listening.
Okay, thank you very much, Shengyu. So this paper is under review in GMD, but the source code is already available on GitHub. So if you are interested in, maybe please just simply send an email to Shengyu and please try the new latest GPU version.